Good morning. In this lecture, we will discuss some overview of NMR spectra. NMR spectra and what is the standard reference used during this NMR spectra, and how the NMR spectra looks when we take some. For NMR spectra, we required about 40 milligram of organic compound. When first you have to prepare the sample in a suitable solvent, that I will tell shortly which solvent are used and why. Then we put that sample to a NMR spectrophotometer. And what is the output? Output of NMR spectroscopy is look like this. You can see here, this is a spectra on a paper. Okay. At the end means at the right end of the spectra, you will see here is a single peak where the delta value is 0. That is because of TMS. TMS is a standard reference used, and we put a very small amount of TMS in the sample when we are going to take a spectra. So this TMS is a standard reference which is used and whose peak appear at far up field. Means that whose peak appear at, say, we consider that as a 0 value. Other peaks are studied relatively with respect to that TMS. How far the peak is appear, we study means we have to take some reference here. So while taking the NMR spectra, when we are going to put a sample in NMR spectrophotometer, in a very small amount, in a milligram, we put a TMS into the organic compound. So TMS gave a single peak at far right side, and we take that peak and we consider that peak as delta 0 value. All the other peaks, they will appear left to this TMS peak, and we generally concentrate on this distance that is known as a chemical shift. How far the peak appears from the TMS peak, that is called a chemical shift. You can see here 4 peaks, and at the top of in the red the values are written. These values are of delta that varies from 0 to 12. So like first peak is at 2.001. So this is the distance from TMS to this peak. So means in a plain graph, when there is no marking and there is no scale is there, we just put a TMS and it makes a scale. TMS is considered as 0. Okay. The question is why TMS is used and what is TMS? TMS is a tetramethylsilane. It's a compound like this, silicon with 4-methyl group. Why we use particularly this compound? Because of its some characteristics which suits our working environment. First is it is volatile. Boiling point is 26.5. As we know that NMR spectroscopy is non-destructive. Non-destructive means we can recover the compound after taking the spectra. Otherwise, in many spectroscopy, you can't get the spectra. You can't get the organic compound back. But in this case, if you give the 40 milligram compound to the technician, after the spectra came, you can get back your compound, if really need. So, this is the main positive characteristic of NMR spectroscopy, that it is non-destructive. The compound will not destroy. Then what about TMS, which we added to the organic compound? We must remove that compound because we want our compound in a pure state. So then the reference should be such that it can be easily evaporated after the spectra is taken, and the standard like TMS that is easily evaporated. That's why we use this, because it is a volatile. It can be easily evaporated. It's 26.5 degrees Celsius, its boiling point. So to just heat the sample, it will evaporate. Second thing is it is inert to most of the reagent. It will not react. It's characteristic that it is, because this silicon and carbon bond is both are of the same family, and this is almost non-polar bond. And non-polar compounds like alkanes, they are very less reactive toward any reagents. Unless and until we provide a drastic condition, they will not react. So this second characteristic is inert to most of the reagent. Third is solubility. It is soluble in most of the organic solvent which we are going to use to take the NMR spectra. Generally, in a sample which is in the solid state, We have an NMR tube like this, and we put this sample into it, about 40 milligram, and then we put some solvent into it to make it solution. Generally, we use the solvent which do not contain any proton, because this is totally the study of proton, H1 NMR. So this study going to detect all type of protons present in the organic compound. It means our reference, okay, that's why our reference, this TMS, that give a single peak because it has a 12 protons, they give a single peak. Why they give a single peak, what are equivalent, that we will discuss shortly. So the solvent must be proton free. We generally use a CdCl3. This is a chloroform, deuterated chloroform. Chloroform is CaCl3, now it is CdCl3. D is deuterium atom, it will not give peak. That's why you use this CdCl3. Almost all the organic compound which we prepare in the lab, they are soluble in CdCl3. If they are not soluble, we will use another solvent, that is DMSO, dimethyl sulfur oxide. This compound is, the formula is like CD3, S double bonds O and CD3. There is no proton. All the hydrogen get replaced by deuterium atom. That's why these solvents are very costly, and each one sample, if you want to get its H1 NMR and C13 NMR, it costs about 500 rupees per sample because of their cost of these solvents. Okay. So these are the solvents which used during the NMR spectroscopy, CdCl3 or DMSO. DMSO is more expensive than CdCl3. So almost 90% organic compound which we are going to prepare in a lab, which are novel organic compound, they are soluble in CdCl3. If not, then we use DMSO. So next, the property of this TMS is that first is it is volatile, can be easily evaporated after we done the NMR spectra, after take the NMR spectra, and then similar to most of the reagent. Soluble in most of the organic solvent. Its property that it is soluble in most of the organic solvent. All the protons are equivalent. There are 12 protons, 3, 3, 3, 3, they are equivalent. You can see the same environment. And equivalent and non-equivalent in detail we will discuss shortly. So that's why they give the single peak. When the protons are equal, they give the single peak. Okay. Non-equivalent protons, they give different peak. If in an organic compound there are 3 non-equivalent protons, we will get 3 peaks in the NMR spectra, as we discussed in last 2 lectures. If in organic compound there are 5 types of non-equivalent protons, then there will be 5 peaks in the NMR spectra. Directly from the NMR spectra, we can come to know how many types of protons are there. Last, the most important characteristics of TMS is that silicon is electropositive in nature. This silicon is electropositive as compared to carbon. Electron activity that decreases down the group. So there is a carbon, then silicon. So electron density is around there, around silicon. So when the electron density is there, then that causes the shielding. Shielding, that is upfield. In a spectra, you will get 2 types of peaks. The peaks which are very near to TMS, those peaks are called upfield. And the peaks which are far away from the TMS, like these values, 10.01, 7.3, they are far away. These are called downfield or de-shielding peaks. Okay. So, what is the difference, how these are prepared, how these are appeared in the spectrum? Now, keep in mind that external magnetic field strength that increases from left to right means towards delta 0 it increases. Upfield means stronger field, higher field. Downfield means weaker field. Because in NMR we studied the theory that there is a gap between the 2 alpha and beta state. This is a alpha and this is a beta state. This gap can be controlled by adjusting the external magnetic field. Because in this NMR spectra we have 2 variables mainly. 2 things are there mainly. One is the radio wave radiations whose frequency is fixed. For any NMR instrument that frequency is fixed. we can't change that frequency of radiation. But what we in our hand is the magnetic field. So the alpha and beta, the difference between these two can be increased when the external field increase, the difference that increases from left to right. Okay, so in our hand is that external magnetic field. When the external magnetic field is increased or decreased, the difference may increase or decrease. So main task is to adjust the distance in such a way that flipping take place. We have to adjust, by controlling the external magnetic field, we have to adjust the distance between these two in such a way that the incoming radiation that may cause flip. Flip means that one proton move from alpha to beta state. When flipping take place, the peak will appear. One flip, one peak. Okay, so by adjusting the external, it means when the external magnetic field is very less, for peak 10.01, external magnetic field is very less, means distance is less. So at this distance alpha and beta, there may be some proton in the organic compound which at this distance they become resonance with the electromagnetic radiation and flipping take place. So there are various types of protons in the organic compound. If we have an organic compound and it has a various types of protons, some protons may flip at lower field strength, some protons may flip at higher field strength depending upon their environment. Why some flip at higher field, why some flip at lower field, that we will discuss after we discuss this equivalent or non-equivalent protons. Then there are some factors which affect these upfield and downfield. Then we will discuss. And induct effect is one of them. So in an inorganic compound which we are going to whose structure we are going to find, they contain large number of protons. Some protons they flip at lower field strength. The peak will appear at downfield. Some protons they become in resonance with the radiation at higher field. They require large energy gap between alpha and beta. So such protons, their peaks will appear upfield. So there are two types of peak we divided into. Upfield means which appear at when you apply a higher magnetic field strength. They are more close to TMS. Keep in mind, upfield shielding means they are more close to shielding and de-shielding, where the next topic we will explain, we'll discuss it in detail. What is shielding and what is de-shielding. So when we apply magnetic field to any organic compound, if that some of the protons which are present in that organic compound, they give peak at downfield, means at low field strength, and some give peaks at upfield, means higher field strength. So upfield means near to TMS, downfield means away from TMS. So there are two types of peak. And the distance at which the peak appear in the NMR spectrum with relative to TMS is called chemical shift. The unit of chemical shift is ppm. Now, here we can write 0 ppm, parts per million. Here you can write ppm. Okay, so this is a chemical shift, like 2.001 is a chemical shift for first peak, and 5.11 is a second, you can say, chemical shift for second peak. Peaks may be different, like you can see here, their height may be different. The further splitting is different, like split into 3, single, no splitting, split into 2, split into 4. So these are there are some factors which cause this splitting or this separation of peaks from one another. So this is working of instrument. As you can see here, the external magnetic field H0 is applied. This is a sample tube in which the sample is there with small amount of TMS or in a solvent like CdCl3 or DMSO. So when sample is put in magnetic field, these are magnetic field M.Sc, and simultaneously radio wave strike on this sample. Now we are going to change the strength of this magnetic field to make the various protons in resonance with this radio wave, because some proton come in resonance at lower field strength, as we discussed in overview of NMR, that upfield downfield is there. So some protons will come in resonance at the lower field strength, some at higher field strength. So we will start from lower field strength and continuously going to increase the field strength, because we can't change radio wave, its wavelength remain fixed. Then which field strength, or what is the strength of magnetic field that we use? So strength of magnetic field which we are using in NMR, that may vary instrument to instrument. What are the strength of this units of this strength? Strength of external magnetic field can be expressed in the form of Tesla, can be expressed in the form of Gauss or megahertz. These are the simple units in which we generally express the strength of external magnetic field. So 1 Tesla is 10 raised per 4 Gauss. Like if we are using how to compare Tesla and megahertz, so suppose I write here Tesla and here megahertz. Now you can see here, okay, sample tube, you can write here, sample tube made up of glass. If we have a 7.05 Tesla, it will be equivalent to 300 megahertz. There are various instruments like 300, 500, 700, 900. So corresponding hertz, these strength of magnetic field you can compare from here, 500 megahertz. If it is 16.45 Tesla, it will be your 700 megahertz. If it is your 21.15 Tesla, it will be your 900 megahertz. These are various instruments available as a lower field strength and high field strength. Suppose we are using the NMR spectrophotometer with 300 megahertz. So the strength of external magnetic field, that will be 7.05 Tesla. You can imagine that how strong magnetic field we are using in NMR, because Earth's magnetic field is just 0.5 Gauss. Earth's magnetic field is 0.5 Gauss. Now you can compare, you can imagine that how strong magnetic field we are using to get the NMR spectra. Like 1 10 to 4 Gauss is 1 Tesla, and we are using 7.05 Tesla or 300 megahertz. So we are using 300 megahertz. Okay. So when the sample is here in a tube and we are striking a wavelength, we are shining a light on this sample, simultaneously we are applying external magnetic field and we are increasing the external magnetic field from low to high. When we increase the external magnetic field, the difference between alpha beta, that keeps on increasing. So some protons become in resonance at lower field, they give peak. Whenever this alpha and beta, like this alpha and beta, there is one proton. When you apply exactly same amount of energy, delta E as the difference between these two, and we can adjust the difference between two by adjusting the magnetic field, as I already told. So when flipping take place, like this proton go to excited state, this is known as a flipping. When flipping take place, a small amount of current is generated around in the wire which is around this tube. This sample tube is surrounded by a thin wire. Whenever flipping take place, a small amount of current is generated. That current is received by this receiver. And then that is amplifier. It is amplified by amplifier. Then it go to recorder and we get a peak. For any one single flipping, we get one peak in the NMR spectrum. So when we are moving, so this is NMR is just like scanning. We have organic compound, we are scanning from one side, from low field strength to high field strength. When we are increasing the field strength, various protons, they come in resonance with light, and when they come in resonance and exactly the difference between these two become corresponding to the wavelength of this radio wave, then flipping take place. Okay, and when the flipping take place, we get a spectra, we get a peaks in the spectra. So as we can see, when the field strength is strong, when we are using a strong magnetic field strength, the difference that increases, and we require more frequency. You can see here delta is equal to mu h naught, delta equal to h nu, so mu become equal to mu h naught by h. So mu is directly proportional to h. H naught is your external magnetic field. More the strength of external magnetic field, more frequency is required to flip the proton from the alpha to beta, because that high field strength strongly hold the proton in the alpha state, that is the more stable state. When the field strength is more, it hold tightly the proton in this more stable alpha state. Then we require more energy to make it flip. That's why frequency used, that will be more. So now in MNR and NMR spectroscopy, what we do is that is designed so that radio frequency is kept constant. That is, at any you can set it at any 60 megahertz, 100 megahertz, okay, 400 megahertz, and magnetic field is varied. On tuning the magnetic field to right strength, the proton flips from one state to another. Okay, just like a scanning. So when you are increasing continuously, slowly when you are increasing the magnetic field strength, various protons come in resonance with this radio frequency, and side by side some peaks going on appear in the spectrum. So in this process, radio frequency is observed, and by this flipping of proton, small electric current is generated in the coil of wire surrounding the sample. And that electric current is amplified and recorded by the recorder that is electrical component of this instrument. Now, this is the overall instrumentation, how the instrument works. Suppose we go with the sample in our hand to the technician for NMR. 40 milligram sample is required. And we must tell the technician in which solvent it is dissolved, either it's CDCl3 or DMSO. What the technician will do, he will put the sample into the tube and add a solvent, 0.5 ml CDCl3 or DMSO4 is sufficient for solution formation, and a very small amount of milligrams at TMS. And put the sample into this tube and in between the magnetic field. That is the part of instrument. You can't see the magnetic field. You just vacant space is there to just insert the tube over there, and then scanning start. After that, by tuning the NMR, that technician will get your NMR spectra, and that NMR spectra give information about the structure of the compound. You have already a structure of the organic compound just to compare which peak is due to which type of protons. So in the next lecture, we will discuss various types of protons, equivalent and non-equivalent, how peaks are appeared, how peaks are splitted, like that, and see how the spectra is formed when a compound is given for NMR analysis. Okay, thank you.